In this example problem, we have a uniformly charged rod of length L. So this is the length L from here to here. And let's say it has total charge Q on it that's distributed uniformly. What we want to do in this problem is find the electric potential at the location of this green X here. So let's say that the distance from the green X to the end of this rod is Y, and that, let's say this is perpendicular right here. So this line here is perpendicular to the rod. We want to find the electric potential here. Now, this thing is not a point charge, so we can't just blindly use the formula for the electric potential due to a point charge to find the electric potential here. Instead, we need to handle this as a continuous charge distribution. So we can modify the formula for the electric potential due to a point charge as follows. That is, the contribution to the electric potential of a infinitesimal chunk of charge dq is just the electric constant k times dq times divided by the distance from dq to the location where we're interested in knowing the electric potential. Note that k is just shorthand for something that's often written this way. K is 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space. Okay, so let's apply this. To use this expression, which we're going to eventually put in an integral, what we need to do is find some prototypical dq along this charge distribution, represent the distance from there, straight line distance from there to the field point with our r, and then set up a function that we can integrate so we can get all the contributions to the electric field. Of course, depending on where you are on this charged rod, there'll be a longer or different r, a different separation from the thing producing the electric potential to the location where we want to know the electric potential. So setting that up as an integrable function is the trick. Alright, so let's get started. So let's look at some little bitty chunk of charge, infinitesimal chunk of charge, dq. We can write that dq, that little chunk of charge, as the charge per unit length, lambda, times the little differential length, dl. Now, what's lambda? In the case of a uniformly charged rod, where the total charge Q is spread uniformly, that is, evenly along the length, the charge per unit length will just be the charge divided by the length. Next, we need to identify our R, which is just this, the separation of the chunk of charge producing the electric potential to the location we want to know the electric potential. Now, we need to figure out how to put this R in terms of something we can integrate. Now, this Y isn't changing, but this thing here is changing. That's basically what we're integrating. We're adding up, taking all the contributions for if this little chunk of charge is here, or here, or here, or here, or here. We want all those contributions. So let's parameterize or find a thing for represent this length right here. So let's call this X. We might as well. Of course, now we've got to make some modifications to what we've written before. I had dq is lambda dl, where dl was some differential length. Now, if I'm representing this thing here by x, then some increment of that, some little infinitesimal of that, would now be a dx. So that's x is our variable of integration. My dq will now become lambda dx. Okay, so we're almost done. We now need to express this r in terms of our variable of integration and of other stuff that's not going to change. We can do that using a Pythagorean theorem. R squared will be x squared plus y squared in this picture, so we can put that in there. So now we're ready to put it all together. I'm going to leave the k as it is because that contains all this stuff. The dq now becomes lambda dx. The r is replaced by this, and we have this expression. Now, keep in mind that the electric potential is a scalar. So what we have here is the contribution to the electric potential at this point from this little bitty bit of charge. All we got to do to get the electric potential at this point from everything is just to sum up all these contributions. That means doing an integral. So integrating both sides, we get so we get this integral. Notice here, let's just look at the units. KQ over L, that has units of electric potential. This is dimensionless, right? dx, that has units of length. X squared plus y squared, but take the square root, that has units of length as well. So there are no units in here when all is said and done. All the units are here. Units are correct. Now let's actually do the integral. I'm going to take the short way. I'm going to just use Wolfram alpha. So here's how you put it into Wolfram alpha. Here's what it gives me. And so we finally, since we have the result for this integral, we can plug that in here and we can get our solution. And again, we note that this has the right units. These are units of electric potential. This is dimensionless. The inverse hyperbolic sine of the dimensionless quantity will be dimensionless. So we've got the right units. And note that this y could have been any value. Not just this particular value, but it could have been further up here or a little bit less. So we actually have the electric potential as a function of y, provided that y is along this direction, perpendicular to the line of charge. So now that we have this result, let's check it out. First, we've checked the units. We've got the right units. These are the units of electric potential. These are dimensionless, so our answer does have the right units. But we can do more. For example, if we imagine this distance y getting really, really long, making that enormous compared to the length of the charged rod, the form of this electric potential as y gets really big compared to the length L should approach the electric potential due to a point charge. To do that, we can examine the approximate behavior of this inverse hyperbolic sine function as y gets much larger than L. And to do that, we can expand this as a Taylor series. So let's see how that works. Using Wolfram alpha for the Taylor series expansion of this function around x equals 0, we get this. Now we note that if x is much, much less than 1, these terms will be really small compared to the first one. So for x much, much less than 1, the inverse hyperbolic sine of x is approximately x. Now consider this. X here is just any argument of this hyperbolic sine function. In the problem we have at hand, that argument is L divided by y. So in our limiting case that we're considering, for really, really large y compared to this length L, in that case, this argument of the hyperbolic sine will be a number much, much less than 1, applicable to this approximation here. So we can rewrite our electric potential function as a function of y as follows. So, plugging in the argument of the function for the function itself is warranted by this approximation in the case where L over absolute value y is really, really small, much less than 1. We plug that in here, and the L's cancel, and we get that the electric potential is approximately equal to the electric constant, K, times the total charge, Q, divided by the distance of the point that we're interested in knowing the electric potential at from this line of charge, Y. This is indeed the formula for the electric potential due to a point charge, so our limiting case checks out.